Hi again. Today we're going to talk about Le Chatelier's principle. This is part one of two videos. Today I'm going to go over all of the principles of Le Chatelier and what it actually means. And then part two is going to be a whole bunch of examples and practice problems. So what we're going to talk about is how equilibriums shift in response to stresses placed on them in order to maintain equilibrium. We're actually going to start with a potential energy diagram review. We're going to take quite a few notes today and do some examples. What I would like you to do in your notebook is draw a potential energy diagram with this given information. Things to include: label the y-axis and the x-axis, and you're going to need an actual scale in order to properly place these. Here's what your potential energy diagram should look like. So this is an endothermic reaction. You were given H reactants, the activation energy, and the enthalpy of the products, or the potential energy of the products. So your y-axis should be potential energy in kilojoules. For your reaction coordinate or time on the bottom, I did a scale by 100 from 0 to 1000. You didn't have to go quite that high. But H reactants start at 500 kilojoules. Your potential energy of the products was 600. And your activation energy was 300, so the very top of your curve should line up with 800. And lastly, just a reminder, this is endothermic because your potential energy of your products is higher than your reactants. Energy has been absorbed. Here's a little recap from our last video, but equilibrium. A system at equilibrium is going to want to stay at equilibrium. What this means is that the reactants and the products have a constant concentration, and the rates of the forward and reverse reactions are equal. However, these equilibrium can be stressed. A stress is a change to the system at equilibrium, and that stress is going to have to be corrected. When I say stress, I mean any change in temperature, concentration, or pressure of the equilibrium system are considered stresses. Le Chatelier's principle. Le Chatelier's principle states that if a stress is placed on a system, so again a change in concentration, pressure, or temperature, the system will shift the equilibrium in a way to relieve that stress. So this is all about how equilibrium are going to deal with stresses. As we just said in a couple slides ago, those stresses to a system are changes in concentration of the reactants or the products, changes in temperature, or changes in pressure. Changes in pressure are only going to affect gases. Equilibrium are going to shift in response to a stress. What a shift means is they're going to favor the forward or reverse reaction. So there's only two ways to shift. A reaction can use reactants to make products or products to make reactants. Reversible reactions, like we talked about in our last video. But when a reaction uses reactants to make products, the reaction is said to have shifted in the forward direction. It can also be considered a shift to the right or a favor of the products. But it's happening in the forward direction like we're used to from reactants to products. An equilibrium can also shift where it's using the products to make reactants. This reaction is said to have shifted in the reverse direction. It can also be referred to as a left shift or favoring the reactants. So sometimes the terminology with these questions can be a little confusing because there's a few ways to say the same thing. Favoring the forward direction, shifting to the right, favoring the products. All three of these phrases mean the same thing. Just like shifting in the reverse direction means shifting to the left or favoring the reactants. And here is a little diagram to show you. Again, reactants go to products. We have the double arrow, but a forward shift is favoring the right direction or the products. A reverse shift is shifting to the left or favoring the reactants. Alright, so now we're going to review what generally happens with stresses. The first one we're going to talk about is concentration. So in a chemical equilibrium, if the concentration of a substance is increased, the reaction is going to shift to use the excess substance. So while I know many of you will want to memorize, oh, this causes a shift right or left, you can't memorize it that way. You have to remember what happens in that scenario. So again, this is kind of your key point right here. If the concentration of a substance increased, the reaction has to shift left or right in order to use that added substance. So for example, our stress, more A is added, so we're going to increase the concentration of A. Now our reaction is going to have to shift to use up what has been added in excess. So the reaction is going to have a right shift in order to make A react with B to get rid of the excess of A. So we increase the concentration of A. Our equilibrium is shifting right or favors the forward reaction. The equilibrium is shifting to get rid of the excess of A. And our results is now a decrease in the concentration of excess A. So our equilibrium is shifting in order to get rid of that new stress. B is also going to decrease in concentration as it reacts with that excess A. And C and D, our products, are going to increase in concentration because we're making more of it. Now with concentration, we can also decrease the amount of substance. So if concentration of a substance is decreased, the reaction is going to shift to make more of that substance. We have to replace what's been removed. So for example, if we remove B, we're decreasing the concentration of B. We now have to replace what's been removed. Our equilibrium wants to stay at equilibrium. It's going to shift back to its original state or as close as it can get to it. So we're going to experience a left shift or favoring the reverse reaction in this case in order to replace B. So let's recap. We decrease the concentration of B. The equilibrium is going to shift to replace what's been removed. Thus, there's a left shift in this example. Our results are the concentration of A and the concentration of B are increased. We're replacing what's been removed of B. And C and D are going to decrease in concentration because they are being used to produce A and B. Our next stress is temperature or energy. So you can really treat temperature or thermal energy very much like a reactant like we just did with concentration. And you'll see what I mean by that in a second. But let's go through our first case. If temperature is increased, the equilibrium is going to shift to remove the excess heat. So if temperature increases, just like if concentration increases, the equilibrium is going to shift to relieve that excess, to remove it. So in this case, heat is on the we have an endothermic reaction, so it's on the reactant side. We increase the amount of heat. Again, we need to use up what's been added. So this is on the reactant problem. We're going to shift away from this to relieve that excess. Temperature increased, heat is added to the system. The system's going to shift so that excess heat is used up. In this case, this results in a right shift or favoring the forward reaction. Our results is the temperature is decreased, so we're removing that stress that had been applied to the system. The concentration of A and B are going to decrease, and the concentration of C and D are going to increase because we are favoring the forward direction. We're making more of C and D. I should also add that as we're making more of C and D, it requires heat, B, and our reactant A in order to do so. So all three of these decrease as these two increase. Our next scenario is if heat is removed from the system or our temperature is decreased. When something is taken away from an equilibrium, you have to replace it. So in this case, we have an exothermic reaction. Heat is on our product side. Heat is taken away. This now has to be replaced. Heat is a product, so it's going to favor the reaction where we are producing heat. So we experience a right shift or a favor in the forward reaction. So our temperature is decreased. The equilibrium is going to want to increase that temperature again. Equilibrium is shifting to replace what has been lost. So for this case, a forward shift is favored. Our result is our temperature is increased as heat is produced from the forward reaction. The concentration of A and B decrease because they're being used up to replace that heat. And the concentration of C and D also increase because A and B is going to produce everything on this side of the reaction. So temperature and concentration act pretty similarly in terms of how an equilibrium is going to react to a change in temperature and concentration. Pressure is a little bit different. Changes in pressure can only affect gases. So if your equilibrium does not have any gases and there is a change in pressure, nothing in your equilibrium is going to change. It's going to remain the same. Gases only here. So you got to be looking for that G in parentheses in your equilibrium in order for this to apply. But here's pretty much what happens. If you increase pressure or you're decreasing volume, remember inverse relationship here, Boyle's law. But if you increase pressure, there will be a shift in equilibrium in the direction that produces the least number of moles of gas. The way to figure that out is you're going to add the coefficients from a balanced chemical equation comparing the total moles of gaseous reactants to total moles of gaseous products. And I'll show you what that looks like in a second. If there's a decrease in pressure, the equilibrium is going to shift in the direction towards the largest number of moles of gas. So really there's two things to remember with pressure. If pressure is increased, you're shifting towards least number of moles of gas. If pressure is decreased, you're shifting towards the largest number of moles of gas. All right, so our first case here, our stress, we're going to increase the pressure. So this means we're going to shift to the least number of moles of gas in our equilibrium. So here we have the Haber process. We have nitrogen plus hydrogen producing ammonia gas. We're going to look at how much or how many moles of gas are on either side of our equation. So if we come here, we have 1 mole plus 3 moles for 4 moles of gas, and then we only have 2 moles of gas on our product side. So we're just adding up the coefficients. 1 plus 3 is 4 moles, 2 moles of gas. If one of these was not a gas, let's say this was a solid, we would only be looking at the 3 moles of hydrogen. Remember, gas is the only thing that matters with pressure. So we're now going to shift towards the least amount of moles, meaning we're going to experience a right shift. So we had an increase in pressure. We shift towards the least amount of moles of gas produced, which is our product side. This equilibrium, for this case, favors the forward reaction. Our results means our pressure increase is relieved, so we have an overall decrease in pressure. Concentration of N2 and H2 are going to decrease as they're used to produce ammonia, and our ammonia concentration is going to increase. And our last slide. So if we decrease pressure, we're going to shift to where there's the most amount of moles of gas. So same equation, Haber process, we have 4 moles of gas. So if pressure is decreased, we're going to experience a left shift towards the most moles of gas produced. Decrease pressure, shift towards the most moles of gas. The equilibrium in this case favors the reverse reaction. Our result is our pressure is increased, concentration of N2 and H2 increase, and our concentration of ammonia will decrease as it is producing N2 and H2. Part 2 will have examples, more examples. If you have any questions, let me know. Have a good one.